Okay, we're going to put this nice looking Simpson 260 through some tests. Let's take a moment just to take a little glance at it. Disconnect it here. It's in a nice shape. Clean, shiny. Seems to be in good shape all around. Handle's in good shape. A few surface scratches from the years of service. Not much you can do about that, huh? But, as we're going to see soon, this unit is in excellent operating shape, and we're going to check it out. Okay, well, you might wonder what the heck I'm doing here. What I've done, the base calibration of this Simpson requires that 250 millivolts provide full scale when you're going in from the common to the 50 microamp input. And when you do that, there's a couple of pots in there, one of which you adjust so that the combination of the meter resistance and that pot provides 5,000 ohms. And at 50 microamps, then you're talking 250 millivolts. So there's our 250 millivolts. That's across that meter right now. And I've adjusted the pot and got that. And I've also fed the 250.05 millivolts through a 10 ohm resistor using this resistor box. And I'm measuring the voltage across that resistor, and right now I'm getting 500 microamps. So 500 microamps across a 10 ohm resistor. And that's telling me that I've got, which means I've got 50 microamps going through it, which is what drives that meter full scale. What that tells me is everything is calibrated properly right now. And I had to go through a couple of iterations of calibration to get it. But I am full scale right now on the 0, and if I remove it, it's going to fall back to, that's full scale voltage. We're going to fall back to 0 on the meter. So that's what I'm up to. Alright, we're done with our calibration. We're right now on the 2.5 volt scale. And as you can see, we have 2.5 volts going in. That's within, oh my goodness, that's 100 millionth. Anyway, we are full scale on a 2.5. That's exactly what we wanted. So let's change our scale to 10. And on the 10 volt scale right now, with 2.5 volts going in, we'd be reading, you're reading the second arc under, but you're reading the lower of the letterings. Middle would be 3, we're running 2.5, so there's 1, 2. Let's go ahead and take her up. I'm adjusting the fluke right now. Let's go 3. Right on the money. 4. Right on the money. 5. Right on the money. 6. Okay, let's take her all the way up. 7, 8, 9, 10. Full scale, right on the money. The cal did the trick. Okay. Going to 50 volt scale. Raise up the fluke here. Let's apply 10 volts. $20, $30, $40, $50. Full scale at 50 volts, right on the money. There is no calibration on the DC voltages once you have the meter adjusted for 50 microamps and that initial resistance set up for the meter to get 250 millivolts for 50 microamps. Once all of that base adjustment's done, then the rest of it's just done with switching precision resistors in and out. So calibration is going to be good here. The best I can show you on the 250 scale is I can take you up to 100 volts. That's the best my, well, that's not true. On DC I can do better. So we'll do that. Let's go up and we will go 100, 200, 10, 20, 30, 40, 50. Right on the nose. Alright, so our DC cal is excellent. Let's take a look at our AC. Bear with me, I'll hook up. Alright, we're now adjusted to AC. We are feeding in a 100 volt AC signal on the 250 volt range. 100 volts is the best I can do on the AC output that I have. But I am reading dead on 100 volts. You read the top red line, the marker, and then you read the lettering, the black lettering that's up above. The top scale reads 100 right now. Alright, so let's go ahead and step it down. Let's try Alright, there's 50 volts. 50. And we've got 50 right on the line. Alright, so let's go ahead and change our range. We'll go to the 50 volt range. And we should be full scale. We are. 50 volts, 50 volts full scale. Let's go ahead and turn that down. Let's go to 20. All right. 20 volts AC, and we are reading maybe a hair above 20 volts here. But 20 volts. Okay, and let's go ahead and take ourselves down to 10. There's 10 volts. We've got 10 volts. Pretty much right there. Maybe a hair above the 10 volt line on that the red that I can see, but it's reading 10 on the lettering. It certainly appears to be 10 volts, and for the 3-4% that we're given on the AC for accuracy, we're good. Let's go ahead and switch ranges. go to the 10 volt range, and we should be 10 volts. We are just slightly over 10 here. So we've let's keep moving. Let's go to 5 volts. All right, 5 volts. We're reading a shade over 5 here, where it looks like, maybe 5.18, something like that. Alright, and then let's take ourselves down to 2.5. Alright, 2.5, and we are reading about 2.5, and if we go to switch to the 2.5 volt scale, we are 2.5 dead on. So it looks good. Let's go ahead and take ourselves to, say, 1 volt on the 2.5 volt scale, and there's 1 volt. And looking at our scale, we are dead on 1 volt. Right on the 1. You read on this 2.5 volt scale right now, the lower. We're dead on. So that does it. We've gone through the AC range, and we tracked very well. Little tiny bit of nonlinearity on the 10 volt range in the mid band, but very small amount. Let's go ahead and check the resistance next. Bear with me. Okay, for this little exercise, all we've done is connect directly to the resistance box. This resistostat has 0.01% tolerance to the resistors and gold-plated contacts on the switches. I mean, it is really a beauty. So I do believe the resistance values that I have on it, we're going to use that as our standard to check the resistive capabilities of this Simpson, which won't be anywhere near what the standard is. So let's go ahead and put ourselves in R times 1. We want to make sure we're reading full scale, so we're adjusting our 0 ohms for full scale deflection. Okay, and we're going to give ourselves a resistance of 1. All right, let's go ahead. There's 1. One. 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, we've tracked extremely well. We're at the 10 mark right now, and we could keep going. Yeah, we will. Let's just. There's 20, 30. 40, 50, 60, 70. Really not much sense in going into the muck over there. Let's go ahead and raise ourselves up to the next range. We're going to go back and check our 0 again. Alright. Yeah, good thing we did. There's our 0. And R times 100. So let's do 100 ohms. 200, 300, 400, 500, no problem. Let's do, that would be 15,000. Well, I want to be able to see this, but a little bit difficult. There we go. Shoot. And let's there's 10,000, 20,000, 30,000, 40,000, and 50,000, and then we head into the muck again. So let's go ahead and turn this back. Looks good. R times 10,000. 0 ourselves here. Okay. And then starting at the 10,000 mark, let's go 10,000 ohms, 20,000, 30, 40, 50,000. 60, 70, 80, 90, 100,000. Okay, there would be 200,000, 300,000, 400,000, 500,000, and in this case you can keep going, but just gets harder and harder to read. So anyway, our ohm meter is reading quite well, and that really only leaves the current ranges to worry about. We know the 50 microamps is working, but it would be the 1, 10, and 100 milliamp ranges that I'd be most concerned with, and we'll try and test those. Okay, we're now measuring current. We're on the 100 milliamp scale. I have a resistor box with a precision 100 ohm resistor in here, the cooling fan, power supply feeding in series through that 100 ohm resistor through the current meter, and then back again to the power supply. And I also have my fluke reading across the 10 ohm resistor to tell me what across the 100 ohm resistor to tell me what voltage I'm dropping on that 100 ohm resistor. And right now I am dropping 1 volt over 100 ohms, which means I've got 100 milliamps running through it, and I am exactly on the 100 milliamp mark on the meter. Now let's go ahead and turn our voltage up on our power supply, and we're going to turn it until we get full scale. Alright, that's full scale, which means we'd be getting 100 milliamps. Let's see how that checks out. Across that 100 ohm resistor right now we have 10.02 volts. Let's call it 10. 10 over 100 is 1/10, which would be 100 milliamps. So you are getting 100 milliamps of current that's readable on this meter. Okay, so let's go ahead and turn this way down. Alright, and then we'll go ahead and change our range. We're going to go to the 10 milliamp scale. And in this case, I'm only going to need a fraction of the prior. So let's go ahead and move our leads to the 10 ohm resistor here. We're going from the 100 to the 10. I'll show you in a second here what I'm doing. There we go. 100 ohm is here. This is 10 ohm. Okay. And let's go ahead and see what we got to do to get full scale again. Very touchy. Alright, there we are, full scale. And we are getting 0.1 volt across a 10 ohm resistor. And that would be 10 milliamps. So we've got it. And let's go ahead . Go the other direction. There we go. We're going to reduce ourselves to the 1 milliamp position. Okay. And we're going to adjust our voltage again. We're shooting for full scale. Full scale. 1.007 volts, and this time it's across a 1000 ohm resistor. So 1 over 1000 is 0.001, which is 1 milliamp, and we got 1 milliamp full scale. So we're accurately reading that. Let's go ahead and cut ourselves down to a half mil. Alright, that would be a half mil right there. And we are getting essentially 0.5 volts over 1000 ohm resistor would be a half mil. So we're tracking excellently. So there's all three current ranges there, doing a beautiful job. We know the 50 microamp did a beautiful job. The only thing left would be 10 amps, which uses a rather large shunt. But let's go ahead and take a look at it too while we're here. Give me a moment. Okay, we've connected ourselves into the negative and positive 10 amp port. We've connected using a series resistor of 1 ohm from the power supply, and we are right now reading 0.3 of a volt across that 1 ohm. So let's go ahead and give ourselves, let's shoot for 2 amps momentarily just to see what we get. There's 2 amps right there. 1.98, 2 volts over 1 ohm is 2 amps. Let's go ahead and give ourselves more. I think I am at my rate of 5 here. There's 5 amps. Right. Maybe not going to reach it. Alright, I'm getting 4.8. I got 4.8 volts across 1 ohm. And I'm getting 4.8 on the dial here, so I'm getting 4.8 amps. That's the most my poor little power supply is going to be able to handle. So, let's try it again. Okay, so we tracked everything very well. The meter is in good cal, working well. It's nice looking. Has a few scratches on the back of it in particular. Nothing terrible. Just years of use. Nice shine to it. Nice handle. Everything works well. I'll throw a set of leads in with it. You're going to have a manual that goes with it. I'll give you the calibration procedure I've written up. You won't find a really accurate calibration procedure. I've got several in here, but the one I wrote up I think is the one that you'll like. I certainly did. So happy bidding. Thank you for listening. A lot of people wonder, why would you want to have a meter like this, an analog meter like this, when you could get certainly more precision and accuracy out of a more modern digital? Well, I'll tell you what. If you're looking at something that is relatively constant in value, and you're trying to get finesse, then yes, the digital can't be beat. But if you're looking at something that's fluctuating, like maybe the output of an amplifier as music is playing, or if you've got a shortwave where you're receiving a signal that's fluttering in and out, then trying to resolve a mess of flashing digits is almost impossible. Whereas looking at the dampened movement of the needle and then averaging it out, you know exactly where you're at. So sometimes this analog meter can be of real benefit. I know when I was aligning the Heathkit shortwave radio, and I was looking at the voltage, the automatic gain circuitry, AGC control, that I was having exactly that problem, and the analog meter was really the solution for me. So, and just about everybody who's ever been in electronics in the last 40 years has seen and used one of these things sometime. They're an antique, but they're an old friend too. So, thanks for listening. Happy bidding. Bye.